Okay, in this opportunity we will talk about the autoionization of water and pH, which it's probably the most important concept to cover with the acid-base equilibria. I mean, for the most part, we are talking about chemical equilibrium, but the autoionization of water and pH is what makes the whole story of acid bases more interesting. So, autoionization of water, what does that mean? If you remember when we were talking at the beginning of the chapter, acids and bases are characterized by, or can be defined as substances that will donate or accept protons, H+. And for that matter, an acid, generally speaking, will be a substance that will increase the concentration of H+ in solution, or the concentration of H3O+, the hydrogen ion. And a base is something that will increase the concentration of the hydroxide ion. Okay, so if you remember then, when you have water, because water is the main conduit here, water is where you are going to dissolve everything, and then water could actually behave as an acid or a base depending on what you are mixing with. If it's an acid, then the acid is the proton donor and water is going to be the proton acceptor. And if it's a base, then the water is going to be the proton donor. So that is if you're mixing water with an acid or a base, but that makes water behave as an amphoteric substance. I mean, when you think of amphoteric, we are talking in terms of dual behavior. And this dual behavior has to do with behaving as an acid or a base, depending on what the situation is. But if water has the capacity to do that, then technically it's also capable of doing that with itself, because water can be an acid and a base with itself. So that's what these couple of equations that we have here are showing you. Again, the more technically correct equation is this one, because it's showing the formation of the hydrogen ion. And remember, that's because the H+ is so reactive in solution that will always be associated with something else, in this case, water. Either one of these reactions would be equivalent. I don't really care if you use H+ or H3O+ when doing your calculations, but I want you to be consistent. If you choose to use H+, use H+ all the time. If you choose to use H3O+, use H3O+ all the time. I might or might not follow my own advice, but that's what I think. Just stick to one of them. Okay? So, one important thing that you need to remember is that when you have pure water without anything else, then the concentrations of those two ions are equal to each other and equal to 1 10 to the negative 7. So that's the native concentration of each one of these ions in solution. Okay, and they are present at all times in larger or smaller concentrations, but whenever you have a aqueous solution, those two ions will always be present. Now, if we are talking about water behaving as an acid and a base, then this is all about acid-base equilibrium, right? So if we go, let's just say that we have water here, and let's be a little more specific. Liquid water can be in equilibrium with its ions, H+, which is going to be dissolved, plus OH-, which is also dissolved. Okay? So that's an equilibrium, and you can write an equilibrium constant expression for that. If that's the case, then K is going to be, remember, this is liquid water, it's a pure substance, and as such, you don't include that in a equilibrium constant. So the constant would be simply the concentration of H+ times the concentration of OH-, right? But because this is the autoionization of water, this constant receives a special name, that's KW. That's the ionization product of water, or is the equilibrium constant, the acid-base equilibrium constant for water. And it has a very specific value. It's 1 times 10 to the negative 14. Remember, in pure water, H plus is equal to OH minus equal 10 to the negative 7. Well, technically it's 10 to the negative 7 times 10 to the negative 7, that's 10 to the negative 14. So that's where that number comes from. And the other thing is that, remember, they are related to each other. They are inversely proportional, which means, remember, they have to be, the product has to be constant, and in order to keep that product constant, then if you increase the concentration of H plus, in order to this product to be constant, then the concentration of OH minus has to decrease. And vice versa, if you increase the concentration of hydroxide, then the concentration of H3O plus or H plus has to decrease. Okay, so that's the ion product of water. Now that gives us a little insight into, if we are talking about acids and bases, then we are going to talk about solutions that are acidic because of the acid, and solutions that are going to be basic because of the base. So our cutoff is 10 to the negative 7. That's pure water. This is your neutral solution. Then concentrations larger than, if we are talking about acids, if H plus is larger than 10 to the negative 7, then it's acidic. If OH minus is larger than 10 to the negative 7, then it's basic. Okay, and then you can establish the relationships there. So what happens with the H plus if it's a basic reaction, the basic media? So if the concentration of OH minus is larger, then the concentration of H plus is smaller. Okay, but the point is, the cutoff is 10 to the negative 7. Concentration of H plus larger than 10 to the negative 7 is acidic. Concentration of H plus smaller than 10 to the negative 7, it's basic. And kind of the same relationship you can establish with the hydroxide ion. So here we have our several cases in which now we are going to use Kw to make some calculations here. So in the first one, we have the concentration of H3O plus equals to 7.5 10 to the negative 5. So the key concept to remember here is that Kw is H3O plus times OH minus. Therefore, if we want to calculate OH minus, then it results that OH minus is going to be equal to Kw over H3O plus. So for A, then the concentration of OH minus is going to be equal to 10 to the negative 14, because that's Kw, divided by 7.5 10 to the negative 5. And this is equal to 1.33 10 to the negative 10. Okay, that is the concentration of OH minus in the first case. In the second case, for B, then the concentration of OH minus, similar expression, 10 to the negative 14 divided by 1.5 10 to the negative 9. And this is going to be equal to 667 10 to the negative 6. 10 to the negative 6. Okay? So in the first case, that concentration of H3O plus is larger than 10 to the negative 7, so this is an acidic solution. In the second case, the H3O plus is smaller than 10 to the negative 7. That is basic solution. And if you compare the concentrations of hydroxide, so in this one that is basic, you have a smaller than 10 to the negative 7 concentration of H3 plus, you have a larger than or greater than 10 to the negative 7 concentration of hydroxide. Now last case, last but not least, you are right down the middle. The concentration is 10 to the negative 7, so this solution is perfectly neutral. The concentration of both are going to be the same. So in this particular case, OH minus is 10 to the negative 7 as well. And let's highlight so that we can keep it all together here. Okay? So the other way around, we can also work it out, right? Once again, Kw is H3O plus times OH minus, right? In this case, we are calculating H3O plus, so H3O plus is Kw over OH minus. So in A, we have that H3O plus is going to be equal to 10 to the negative 14 divided by 1.5 10 to the negative 2, and this is equal to 833 10 to the negative 13. Because of that, the concentration of OH minus is more than or larger than 10 to the negative 7. The concentration of H plus is smaller than 10 to the negative 7. This is a basic solution. And in B, or for B, H3O plus is equal to 1 10 to the negative 7, which means, well, there is not much to do here, right? Because this is, yes, it's 1 10 to the negative 7, because the concentration of OH minus is also 10 to the negative 7, right? So this is a neutral solution. Last but not least, in C, the concentration of H3O plus is going to be 10 to the negative 14 divided by 8.2 10 to the negative 10, and this is going to be 122 10 to the negative 5. Okay, in this case, this is an acidic solution. The concentration of H3O plus is larger than 10 to the negative 7. Okay? Now, in order to have these numbers, or to have an easier way to compare the acidity of different solutions, then we use the pH scale. And the pH scale is just a transformation, a conversion that we do on that concentration to take that power of 10 kind of concentration into something that is easier to handle. And to do that, we take the pH. This is the normal expression of pH, so it's the negative logarithm of the concentration of H3O plus. Okay, that means that, for example, if you take pure water, and in pure water the concentration of H3O plus is 10 to the negative 7, once you take the negative logarithm of that number, you obtain 7. So then we call that, let me rewrite this different way. A neutral pH is equal to 7. Okay, neutral because the concentration of H3O plus and OH minus are equal. Okay, so now we select our scale of pH based around this number 7. So less than 7 is acidic, and larger than 7 is basic. Okay, remember, this is pH. pH refers to the concentration of H3O plus. And yeah, actually, if you have the pH, then you can go back to concentration, and all you have to do is take the antilog of the pH, which basically takes you to take 10 and raise it to the power of minus pH. Okay, so these are two basic equations that you're going to be using a lot in this chapter. And before we get there, so some common pHs of solutions that you may know, probably may be surprising or not. I mean, the acid on your stomach is between 1 and 3, and whether you believe it or not, it's more acidic than most of the things that you can possibly eat. Not even soft drinks that are here have a lower pH. They are not as acidic as your stomach, and it's required because in order to break down the food that you are eating, then you require that kind of media to be able to do so. Okay, so what does these numbers imply? So we have a scale that goes from 0 to 14 in the pH scale, and each number refers to a power of 10. So for example, 0 refers to the power of 0. So we are looking at a high concentration of acid. This is basically 1 molar. Okay? And in the rest, each number in the scale of pH is referred to a power of 10. So that gives you an idea of, okay, around what concentration we are talking about. If you take, for example, 10, right? So pH 10 means that the concentration, or pH around 10 means that the concentration of H3O plus is around 10 to the negative 10. Okay, so it's sort of a quick reference. So like it gives you sort of not such a ballpark figure in terms of where the concentration is. It's kind of precise actually, within an order of magnitude or so. So now we are to calculate pHs in this case, correct? So how do we use these numbers? So in this particular case, remember, pH is minus log of H3O plus. So in this first case, pH is going to be equal to minus log of 1.8 10 to the negative 4, and this is simply 374. Okay, it's a pH that is lower than 7, so this is an acidic solution. If you have the concentration of hydroxide, you still can do it. Okay, you still can do it because concentration of H3O plus is equal to 10 to the negative 14. In this particular case, divided by 1.3 10 to the negative 2, this is equal to 769 10 to the negative 13, and now this is the number that you plug in that equation. So pH is the minus log of 769 10 to the negative 13, and this is equal to 1211. Okay, a pH that is higher than 7, so this is a basic solution. Okay, so in this particular case, it's just, again, plug in the numbers. The pH here is going to be minus log of 9.5 10 to the negative 9, and this is going to be equal to 8.02. And in this case, you can even, since you know how to calculate the concentration of H3O plus from OH minus, okay, H3O plus is equal to Kw over OH minus, then we can actually plug in into that equation. So pH is going to be minus log of 10 to the negative 14 divided by 7.1 10 to the negative 3, and just one step, correct? So this is 1185. So in this case, both pHs are above 7, so this is a basic solution. Now if we want to go the other way around, in which we want to calculate the concentrations from pH, then it's actually probably a little simpler. It's just about how good you are with your calculator to put entering these numbers. But in the first case, since the concentration of H3O plus is going to be equal to 10 to the minus pH, then in this case concentration of H3O plus is equal to 10 to the minus 480, and this is equal to 158 10 to the negative 5. And in the second case, H3O plus is equal to 10 to the negative 837. And when you do this operation, you obtain 427 10 to the minus 9. And you are calculating concentrations here. So for the most part, the calculations, we always leave the units out. But since you are calculating concentrations here, whatever you do, if you're doing pH or anything else, you are always obtaining molar concentration. So don't forget about that. Now we're referring this to pH, but pOH, you can do exactly the same thing, but working with a hydroxide ion. So pH is equal to minus log of H3O plus. Well, pOH is the same thing, minus log, but of the other ion, OH minus. Okay? So in that regard, you can say that we have the pH scale and the pOH scale. You actually don't need two. You can use just one of them, but this is the relationship that you see here. Here, the acidic media or the acidic solution means you have lower pHs or higher pOHs. Okay? So here is low pH, high pOH, and this is acidic. Okay, that doesn't really matter what scale you're using, but remember that the behaviors are opposite. And for basic, you have high pH and low pOHs. These are basic solutions. Okay, remember, two scales to represent the same thing, but they are going in opposite directions. So do not forget about that. Now, there is an important relationship between pH and pOH, and that is, let's start at the beginning, right? Kw is H plus OH minus, or H3O plus for that matter. So what if we take this expression and then we take the minus log at each side of the reaction, at each side of the equation? So we have minus log of Kw minus log of H plus, or H3O plus, minus log of OH minus. So by definition, this is pH. By definition, this is pOH. Okay, and minus log of 10 to the negative 14 is equal to 14. So 14 is equal to pH plus pOH. This is a fundamental relationship that you need to know to work these problems. It can make your life easier, so we are aiming for that, correct? Since we've taken the negative log of the constant here, well, that's something that we also use to make our life easier when it comes to compare acidity constants or basicity constants, because you can do that with every single equilibrium constant. Particularly here for our case, and there is a little mistake here, this is supposed to read Kb, but this is in order to make your life easier. Okay, the pKa is equal to the negative log of Ka, and you process this in pretty much the same way that you process the concentrations. Okay, so the calculations are similar. It's the minus log of 10 to the negative something, or if you want to calculate the constant, then is 10 to the negative pK to the corresponding pK. Okay, so it doesn't matter if it's an acid or a base, the process is similar. Okay, the thing that you have to remember here is that whenever you are converting the Ka to pKa, and let's stick with that for now, the larger the value of Ka, the smaller the value of pKa. Okay, so stronger acids will have that behavior: larger Ka, lower pKa, and of course, lower Kas means you have larger pKas, and that goes for weaker acids. The relationships are pretty much the same if you are referring to a base. Okay, but again, for now we are focusing our attention on acids, so we're gonna stick with acids for a while. We're gonna start doing the calculations for equilibrium situations with pH, and then we will move into bases. Okay, but for now, I want you to remember these trends. Let's call it trends. Stronger acids will have larger Kas, smaller pKas, and weaker acids will have smaller Kas and larger pKas. Okay, so this is call it an artifact. That pKa is an artifact that will allow you to make quick comparisons, okay, without getting lost in the numbers of how larger or how. It's easier if you have those numbers in that simpler scale. It would be easier to make comparisons really quick. Okay, so that's what we are aiming for when using pKas. Okay, so that's it for